So folks, we're going to work the remaining examples now in this video, but I want to point out a couple of quick things, a couple of quick errors that I've made. If you look back at your number 8b, I have an error here. I should have put k plus 1, and in my original video I did not. So this should have been k plus 1, and you can check that. When k is 0, we needed to get the number -1. And so if we do 0 plus 1, then we would have -1 to the first power, allowing that -1 to express itself. So that should have been k plus 1 there, and again there, and there on these questions. So I apologize for that. I'll try to get the video fixed, but I don't know if I'll be able to. So folks, what remains is a few lingering examples looking at how to differentiate power series and how to shift the indices of power series. So we'll look at that over the next couple of examples. The first thing we want to do is we want to take the derivative of that Taylor series that we built. So we've said that this Taylor series right here is the Taylor series of the cosine of x centered at x equals pi. So because this Taylor series equals the function that generated it through something we didn't prove, we can say that we're taking the derivative of the cosine of x. Now I know everyone knows how to differentiate the cosine of x, but what I'd like to do is I'd like to differentiate its Taylor series centered at x equals pi. As you remember, I said that we could think of a Taylor series as sort of like an infinitely long polynomial. And in that sense, the rules of differentiation and integration sort of fit with how you differentiate and integrate polynomial terms. So remember, if I asked you to take the derivative of the term x to the n for n not equal to 0, what we'd get is that derivative is nx to the n minus 1. And so here I've got a power term raised to some power, and we want to differentiate it. So that's going to essentially work like this expression. Of course, one thing to be careful with is it says for n not equal to 0, and we start out our power series with a power of 0. So you can see already that we can't just proceed blindly through our differentiation of Taylor series. So my recommendation is to go ahead and write out the first 2 to 3 terms of the Taylor series, and then go ahead and give yourself a formula for what you think the derivative is, and then adjust that formula accordingly. I think that's the best way to go ahead and come up with the derivative. So let's go ahead and take a look here. When n is equal to 0, this power series, if n was equal to 0, this power series gave us -1, and then when we had n equal to 1, we got the term 1/2 times x minus pi to the second, and then for the third term we got -1/6 times x minus pi to the 4th power. Oops, I'm sorry, that should have been -1/24 plus all of the other terms. And so the reason why I'm showing this is because if we were to go ahead and take the derivative of this, then we can identify what those terms should look like. When you take the derivative of a constant, you should get 0, and that's part of the trouble that I'm trying to discuss right now. And if you take the derivative of the next term, you would get plus just x minus pi to the 1st power, and if you take the derivative of the second term, you would get -1/6. Let me write it down here. -1/6 times x minus pi to the 3rd power, and then plus a bunch of other terms. So we want to make sure, this is kind of a, I don't know, in a way sort of cheating. We know what the answer should be, and we give ourselves a Taylor series, and we just confirm that it gives us the terms that we want. So what I would like to do is let's sort of naively just go ahead and put the sum, and I'm not going to put any indices on here, and we'll just take the derivative of this expression inside the summation as we normally would for a polynomial. So notice that as far as the polynomial is concerned, this whole expression here is a constant, and so so that constant just comes along for the ride. We'll have this, and then when we take the derivative of x minus pi to the 2n, it'll be 2n times x minus pi to the 2n minus 1. So what we want to make sure when we initially set up our index is that it's giving us terms from the derivative that we expect it to. Notice, don't write this down, notice if I were to put n equal to 0 here, I'd run into some trouble because if n is 0, this would give me 2 times 0 minus 1. I'd have x minus pi to the negative 1 power, which shows up nowhere in the derivative of the terms of this power series. So I can't start my index at 1. Instead, I can't start my index at 0. Instead, I'll start my index at 1. And we should just verify that when I start at 1, I start getting terms right away from this power series. So if I were to let n be 1, this would give me 2n minus 1, which is just x minus pi to the first power. Here, this would give me a minus 1 squared if n is 1, which is 1. And in the denominator, we'd have 2 times 1 factorial, which is 2. We'd also have a 2 in the numerator. And so we end up with just a 1 for that coefficient, which is sure enough what we've got there. Likewise, if we were to let n be 2, this would give me 2 times 2 minus 1, or to the third power. And this is beginning to correctly give all of the terms of this Taylor series, which is the derivative of our original Taylor series, with the exception of this very first term, which is 0. And so we just collect that off to the side, like so. So this works as the derivative of cosine of x. It works as the derivative of this Taylor series. Usually what we then do is we do an adjustment of the indices. First of all, and we're still going to infinity. First of all, I'm going to drop off this plus 0 term because that's not contributing anything to the expression. So then I'll have the sum from n equals 1 to infinity. Notice here that there's some canceling that can occur. And just to spell that out a little bit more clearly, we would have 2n in a numerator, plus we've got some other factors, but multiply to it, but we've got a 2n in the numerator, and in the denominator we have 2n factorial, which is the same thing as 2n times 2n minus 1 times 2n minus 2, dot, 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 right? So in the numerator, or sorry, as far as these two terms interacting goes, we have 1 over, and the 2n's cancel, and we'd have 2n minus 1 factorial. So this gives us negative 1 to the n plus 1 all over 2n minus 1 factorial. And then we have x minus pi to the 2n minus 1. So this also works as being the derivative of this Taylor series. And in a lot of ways, I'd be fine with you keeping your answer there. But for what we want to do as we continue to work with this is we want to shift the indices. And so now's a great time to practice this, and we'll do some more practice on the next page. So if I want to shift the indices, it's customary to start a Taylor series at n equals 0. And so the way you shift indices, in my opinion, the way you want to think about it is kind of give yourself what you want for your index counter, but then adjust the expression up above so that you still are generating the correct terms. So the way I like to think about it is here I've subtracted 1 from the index, and so I'm going to add 1 inside this expression here. Let's do that, but be careful. When I add 1 to n, it has to happen right here, n plus 1 minus 1 factorial. And I'll add 1 to this expression here, so I get negative 1 to the n plus 1, and then plus the original 1, so that's easy to simplify, plus 2. And then I'll add 1 here, and be careful, folks. I want to add 1 to n, so I have 2 times n plus 1 minus 1. And so if we clean this up, having added 1 to n inside that expression, we end up with the sum from n equals 0 to infinity. In the denominator, we'd have 2n plus 2 minus 1, which is the same thing as 2n plus 1 factorial when you clean that all up. So 2n plus 2 minus 1 is 2n plus 1. And then we would have x minus pi. Here we'd have 2n plus 2 minus 1, which is 2n plus 1. And the only thing I want to do is, because if I add 0, if it went in as 0, this is going to give me negative 1 squared. I'm always going to get these I'm going to alternate signs with these, I would be fine with just leaving this as -1 to the n, although you could leave that as +2. So if you left it as +2, that's fine. If you said, well, that's always going to be the same as just n, that's fine as well. And here what we've done is we've taken the derivative of our Taylor series, but we did look at the terms of the Taylor series and its derivative, and we confirmed that that's what we were getting as we did basically the power rule for polynomial differentiation, giving us an expression like this. If you're feeling good to hear, great, you're doing good. The next thing we need to do then is work on shifting the indices, and again, my strategy is to give yourself what you want down here, so we make that n equal to 0, and then we compensate, since we subtracted 1 from n in the index, we compensate by adding 1 to n inside the formula. So let's go ahead and look at the next example. We're going to get to chance to practice this again. By the way, I thought this was a nice time to give you a bunch of the standard Maclaurin series, meaning centered at 0, Taylor series of kind of the standard functions that you see in Calc 2. Of the ones that we're looking at, these are, of course, the ones we'll see the most in this particular course, although you want to know all 4 of these. And there's more listed in a standard textbook. So let's practice shifting those indices again. So again, what I'd like to do is I'm saying we want the counter, in this case we want to start it at 4. So I'm going to give myself what I want in the counter. Notice if I had a finite sum, like if this were to, you don't have to change this, but if this were to 3, then I would do 3 plus 4, and I'd now be going up to 7. But because our series is, we're thinking of it as an infinite, well, we've got an infinite series here, so it'll still be infinity. So, as I said, you give yourself what you want for the index, and then you compensate by now subtracting 4 inside here. So that would just give us n plus 3. Folks, if I were to do this again, I would make sure something happened like we saw last time, where we had one of those 2n's. Remember that if I had 2n plus 5 or something like that, and I added 4, or I subtracted 4 from the index, I would do 2n minus 4 plus 5 as I adjust that. So just be careful. But here I have done what was asked of me. I adjusted the counter so that it starts at 4. I highly recommend that you always just double check that the first couple terms of the series agree with one another after you do a shifting. And you can confirm, if I let n be 4, I would have, say, 7 factorial down here, which is the same thing in this construction of the series. If I let n be 0, I still have 7 factorial. And everything else aligns as well. So this is something we're going to do a whole lot in this course, which is we need to add together 2 power series. And so my trick, I think, is the thing to remember when you're adding together these 2 power series. First, get the powers to agree, and then shift their indices. So if we look at the powers here, when n is 2, this is going to start at 0. And here, when n is 0, this is going to start at x to the first. So I want, this has an x to the 0 as its first term, this has an x to the first. I want them to agree, so I'm going to take away one of these terms from here. So I'm going to pull out the term when n is equal to 2, so that everything's starting at the first power. So when n is equal to 2, we have 2 times 2 minus 1 times c sub n times x to the 0. So let's just write that out. We have 2 times 2 minus 1 times c sub 2 times x to the 2 minus 2 plus all of the other terms. So that was the very first term of the power series. We just peeled it off, and so now we'll start the counter at 3, and we'll have all the remaining terms, n minus 1, c sub n, x to the n minus 2. So now if we look at adding these 2 power series together, although we're still not ready to combine them, notice that they start with the same power. Here, when n is 3, I get x to the 3 minus 2, which is x to the first. And for this term, when n is 0, I get x to the 0 plus 1, which is x to the first. So I've got the powers to agree first, then I adjust the indices. So now I want to add these together, and it doesn't matter which way I go. I think I'd like to, it's customary to have your indices start at 0. So I'm going to subtract 3 from my counter here. So I'll just do plus the sum from n equals, subtracting 3 would be 0 to infinity. And so I compensate. If I'm subtracting 3, I'd be adding 3 inside of here. And we still have this term. And let me clean this up. This would be 2c sub 2 plus all that. So the original expression is equal to this, which is equal to this. So we get this extra 2c sub 2. And notice now I have two power series. They both have the same starting power term, and they have the same index. And so we can combine them together through the associative property. So we can say this is n equals 0 to infinity of, and then we'll put a big old bracket, n plus 3 times n plus 2 c sub n plus 3 plus c sub n, and we factor out the x to the n plus 1 in front of those coefficients. And so this whole thing, if you need to, you don't need to put this grouping symbol in there, but just to clarify, that whole thing is sitting inside the series. But the idea was these both had a common factor of n plus 1, and I pulled that factor out. See, x to the n plus 1, and I pulled that common factor out. And so what I've done now is I've combined these two power series together. And again, to keep you from spinning your wheels, I say first get the powers to agree, then adjust the indices. If you try to do it in a different order, you may be able to get it to work, but sometimes you end up undoing the work that you've done, and you make a mess for yourself. Okay. Finally, we have this useful property, and this just says that if you know that the polynomial is identically equal to 0, the only way that can happen, if it holds for all x inside your interval of convergence, the only way that can happen is if all of the c sub n's are equal to 0. Each coefficient is 0. That's, so for example, if I say, if we've got, say c sub 0, x to the 0 plus c sub 1, x to the 1 plus c sub 2, x to the 2. If this is always equal to 0 for all x, the only way that could happen is if each one of these ci's is 0. That's the only way this could always be 0 for all x. So that would be the final property that we'll be using in class. So folks, this is a very, very long pre-work. I hope that this at least gave you a good review of power series. If you're feeling overwhelmed right now, don't worry. We're going to get some more practice at it. And I will say that this is a necessary skill for this course, but it's not something that a whole lot of work is going to be built on top of. So please don't be panicking at this point, but please continue to work with this material. Let me know what your questions are. Thanks for your patience.